Hello everyone and welcome to video number 2 for the topic 5.2 Hess's law. In this video I will be covering the enthalpy changes of reactions determined via enthalpy change of combustion energy cycles. I will explain this using the following equation here. I've given an example. Reactant A reacts with 2 moles of reactant B to produce 1 mole of reactant C and 3 moles of reactant D. The question will ask you to determine the enthalpy change of the reaction, as shown here, using enthalpy changes of combustion values. Thus, if you are given enthalpy changes of combustion values for both reactants and products for a particular reaction, as shown here, one can construct a combustion cycle to determine the enthalpy change of this reaction. Since the enthalpy changes of combustion values of many substances in different states are listed in table 13 of the data booklet. If some are not listed in that table, it would be given in the question, and then unless the question is asking you to determine it. Thus, let's get back to this equation here. Since we are given the values for the enthalpy of combustion of 1 mole of A and 1 mole of B and 1 mole of C and 1 mole of D in the data booklet, I can construct an enthalpy change of combustion energy cycle in which if both moles of 1 mole of A and 2 moles of B were combusted completely, they would both produce CO2 and H2O in specific molar ratio. Since the elements that make up, or the atoms that make up the products, are the same as those in the reactants, combusting 1 mole of C and 3 moles of D completely would also produce the same amount of CO2 and H2O moles, and thus the cycle can be linked as shown in this cycle here. To construct energy cycle is called method 1. There are 2 other methods which we can use to determine the enthalpy change of reaction, which are based on energy cycles. Thus, if the students understands the energy cycles, they would have a really easy time understanding method 2 and method 3. Since the combustion is from when 1 mole of A is combusted completely, it would form CO2 and H2O. Thus, I can draw an arrow from A towards CO2 and H2O as the enthalpy change of combustion definition states, and I would multiply the enthalpy of combustion of A by 1, since there's only 1 mole of A being combusted here. The second reactant, we are combusting 2 moles of B, and since we are given the enthalpy change of combustion of per mole of B in the data booklet or by the question, we need to multiply this value by 2. We are also given the enthalpy change of combustion of C, and since there's 1 mole here, it's multiplied by 1, and we're given the enthalpy change of combustion per mole of D, but since there's 3 moles here, the enthalpy change of combustion of D is multiplied by 3. We need to move through the cycle, as Hess's law states. We could find an alternative mechanism or pathway for the reaction through which we can calculate the enthalpy change of reaction using experimentally or previously determined experimental enthalpy changes of reactions, such as the enthalpy change of combustion values here. As stated in the previous video, the direction of the arrow, if you flip or move against an arrow, the sign of the enthalpy change of combustion would need to be flipped as well. Thus, we constructed a cycle here in which we can move from reactants to products as the enthalpy of reaction here requires us to do. It's to go from 1 mole of A reacting with 2 moles of B towards 1 mole of producing 1 mole of C and 3 moles of D. We would move through the cycle in this direction to determine the enthalpy change of reactions. Thus, we would move along the cycle in this direction here. Thus, we would react A plus 2B to form CO2 plus H2O, which are both combustion values, and we would move with the arrows. Thus, we would keep the signs of these combustion values as is, and since they are combustion values, they would remain negative. But on the other hand, once we reach this intermediate here, to form these compounds from CO2 and H2O would be the opposite of the definition of enthalpy change of combustion, and thus we would have to move against these arrows here, and we would flip their signs. Therefore, the enthalpy change of this reaction would be the enthalpy change of combustion of A, and I would add to that the enthalpy change of combustion of B multiplied by 2, and I would subtract both the enthalpy change of combustion of C and the enthalpy change of combustion of D multiplied by 3 from this value, because these values are going to be flipped. Thus, if this were a negative and this were a negative, multiplying both by negative would produce positive values, deeming them endothermic instead of exothermic, which is the opposite of combustion reactions. This I've stated below. Here, the enthalpy change of reaction ongoing from reactants to products through the constructed cycle using experimentally determined enthalpy changes of combustion values would always look the same and would produce, basically it's going to be the enthalpy change of combustion of reactants here, A and B, multiplied by their equivalent number of moles, subtracted from the sum of both the enthalpy change of combustion of C and D, which are the products. Thus, the general rule when given enthalpy changes of combustion values to determine the enthalpy change of a reaction, we would always construct such a cycle which would produce the following delta H of reaction equations. You will always be subtracting the sum of the enthalpy change of reactants from the sum of the enthalpy change of the products here. This negative sign is added to indicate the flipping of the arrows, since we would move from reactants towards the intermediate and then from intermediate to the products, and thus this movement here from the intermediates to the products would involve changing the sign of this reaction, and this is what this negative sign here would do. The function of it is to flip the sign of the enthalpy changes of the products, this negative sign here. This would be better illustrated using an example. I have added an example below to solve with you guys. And I will solve it using method 1, which is constructing the cycle. Method 2 is this equation here. It's the general equation for calculating an enthalpy change of a reaction when given enthalpy changes of combustion value of both reactants and products. Thus, one can directly plug in the values here instead of constructing a cycle, unless you are asked to construct an energy cycle here. But it's clear that the method 2 equation actually stems from the cycle we constructed here. Thus, all methods are based on this cycle here. I'm going to use the cycle method, the energy cycle, to solve this question here. Thus, this question states to calculate the enthalpy change for the following reaction given the data listed below. We are given enthalpy changes of combustion value determined experimentally, or you might be asked to get these values from table 13 in the data booklet, but in this question they have been listed. I have the enthalpy change of combustion of the reactant C4H8. I'm also given the enthalpy change of combustion per mole for the product C4H10, as well as the enthalpy change of combustion of the other reactant, which is H2 gas. One thing to note is this reaction is a 1:1:1 ratio, and thus I wouldn't have to worry about multiplying the enthalpy changes of reactions by any other moles. The first thing to do to construct this cycle here, would be to place CO2 and H2O intermediates, since we're using combustion values, or we are given combustion values, plus H2O liquid. The CO2 and H2O should be balanced with the C4H10 as well as the C4H8 and hydrogen, but in order to do so, one would have to write the enthalpy changes of combustion of each one of these and calculate them, as I will do in I will show you how to do this in next week's video. Which will involve calculating enthalpy changes of reaction using the third method, which is manipulating chemical equations. Thus, let me continue this example. Since I'm given enthalpy changes of combustion values here for both reactants and products, I place CO2 and H2O at the bottom, which will represent my intermediate to provide an alternative route for the reaction. I'm given the enthalpy change of combustion when 1 mole of C4H8 is completely combusted into CO2 and H2O, and the value for this is negative 2717 kilojoules per mole, and what I have here is 1 mole, so I'm fine. I'm also given the enthalpy change of combustion when combusting 1 mole of hydrogen gas into H2O, and since it's 1 mole here, I don't have to worry once again about multiplying the enthalpy change by any other factor. This is a negative 286 kilojoule per mole. I'm also given the enthalpy change of combustion of C4H10, the product, to convert 1 mole of C4H10 into CO2 and H2O by combusting it completely in the presence of oxygen. The value for this per mole is negative 2877, and thus once again I do not have to worry about multiplying this by any other factors since I have 1 mole ratio here. Now to calculate the enthalpy change of reaction on going from reactants to products, I would have to find another route through the cycle, and my route here would be to go from these reactants to these products through the cycle, which is in this direction here. Therefore, I'm gonna move along this arrow here, and thus wouldn't have to change its sign, and I would have to move along this arrow here to reach the intermediate, and I wouldn't have to reach this sign to change this sign. Then from the intermediate I would form the products, and thus I would be moving against this arrow in the cycle, and thus this needs to be changed into an endothermic reaction, since in this direction it's negative, but in the opposite direction it's a positive endothermic reaction. Therefore, the enthalpy change of this reaction can be calculated using or as follows. The delta H of this reaction would equal to negative 2717 plus minus, which is a minus 286, and I would put a minus here to change the sign of the negative 2877 value. This is a clear application of the equation I listed previously, which is the delta H of reaction would equal the sum of the enthalpy change of combustion values of reactants minus the sum of the enthalpy change of combustion values of the products here. In videos to come, probably next week's video, once we learn the third method for calculating the enthalpy change of reactions using Hess's law, I will cover more examples and this would be clearer. Please attempt the attached worksheet that covers calculating the enthalpy change of reactions when given enthalpy change of combustion values. Thank you for watching.